Thank you very much, Antonio, for giving me this opportunity to report on graphene-based detectors. And thanks all of you who joined this seminar today. As already explained, it's more like a tutorial to introduce this part of our HERMES activity. The outline of the talk is like this. So I will first talk about terahertz detectors, what must be peculiar for them. I will briefly introduce graphene, why is it useful here. Most of the time I will talk about rectification principle to detect terahertz using graphene. But in the beginning I will introduce what is photoresistor and what is rectifier. Not to be confused probably with photodiode. This will be seen from my talk. So again, I will introduce main-based detector, graphene-based detectors, the works done there. Sorry for probably mentioning too many of my works, but it's easier for me to talk about those because I know a little bit more about what was published with my name among the authors. And very briefly, I will make a summary, talk about perspectives, and hopefully answer your questions. Okay, so I start with showing this chart, illustrating what is some frequency range. And I show the frequencies in terahertz, and I show the wavelengths in microns. And on this chart, I show visible range, something that we detect with our eyes. So I really like the picture because it shows how much actually how big part of the visible range is taken by red light. And actually on this scale, visible range is very small. And if I add terahertz range, it takes much more space here. I want to talk a bit about energies and the evaluation of energies corresponding to light quanta for different frequencies and length scales. So boundaries of this large region from 10 gigahertz to 1 terahertz to 1 whatever it is, 1000 terahertz. So I think it's penta, but whatever. So temperatures corresponding to this range go from 0.5 Kelvin to 50,000. So visible range corresponds to very high temperatures, actually several times larger than temperature of the sun's surface. So room temperature on this scale corresponds to the upper boundary of terahertz range. And actually all the HERMES project has to do with frequencies. They're actually somewhere around this particular one. It's almost 6 terahertz. We think our device will work around 3 terahertz, so it's below room temperature. I'm not talking much about HERMES concept here. What I talk about is the terahertz detection in general, and why do we want graphene there. So that's one thing. And the energy of terahertz radiation and its relation with respect, its evaluation with respect to room temperature defines the detection mechanisms. I will discuss them, of course, later. It will be a significant part of my presentation. One thing I want to say right now is that semiconductor industry is important for visible range photodetectors, for near-infrared photodetectors. And it doesn't work for terahertz, mostly because of temperature, a little bit because of lack of appropriate materials. And that's what explains the first thing that people tend to ask. So graphene has no band gap. Why do you want to use it in detecting radiation? So gap doesn't help to detect terahertz. That's the basic message here. Now, if we look on the upper bar on this chart, which talks about wavelengths, we see that the wavelengths of the radiation we want to detect is sub-millimeter, but it's many, many microns. And the structures we want to work with are relatively small because we want sensitive detection, we want fast detection, and that imposes certain restrictions onto the size of our sensitive element. And it's much smaller than the wavelength corresponding to terahertz radiation. Therefore, we inevitably, in most cases, want to use an antenna. And we don't go into details of the antenna design, antenna impedance, whatever. For us, it's more like metallic structure that complements our structure, our sensitive element, to something that has size of approximately comparable to the wavelength of terahertz radiation. In other words, antenna is a metallic structure that couples our sensitive element to the radiation that has much longer wavelengths. Now, what we want our detector to do, we want to convert the radiation into voltage. Every sensor we use in our life, not every, but whenever we think about chemical sensors, sound sensors, whatever sensors, we want them to convert the external stimuli into voltage, because voltage is very easy to digitize and then to numerically process with our computers. So we have antenna, we have sensitive element, we have some circuitry probably to convert radiation to voltage. And this conversion is based on certain mechanisms here. These mechanisms can be pretty sophisticated. So here I show just antenna connected to some black box that converts something to voltage. Here I show that we can have more electrodes going to our sensitive elements in order to convert the response to radiation into voltage, like be it temperature or be it something else, maybe expansion. And here I give two examples of things that are very, very sophisticated and too complicated for what we want to do, but make pretty sensitive detectors of microwave or terahertz radiation. So it's Galilei cell and ferroelectric detectors. So for Galilei cell, radiation hits the gas actually, and then gas, due to pressure, deforms some membrane, and this is converted to change of signal of a photodetector that detects light, visible light or near infrared light reflected from this membrane. So it's very complicated process from radiation to actually voltage. Still, we have voltage at the output. For pyroelectric, it's a little bit simpler, but once again, radiation is converted to heat, heat is converted to polarization, polarization is converted to voltage due to certain circuits present here. So, in fact, we want something much smaller, simpler. And before we describe what it is, I want to talk about key characteristics of detectors that we care about. As I said, we want to convert radiation into voltage. So the voltage, we want this voltage to be proportional to radiation intensity. That's what happens in most cases within certain intensity range. And in this respect, the important characteristics of our device is the responsivity, which we express as ratio of the output voltage to the radiation intensity. We need to know it in order to understand what is intensity of the radiation that we are detecting. Another, maybe more important characteristic is noise equivalent power. I don't go into details where it comes from, but importantly, it's related to the noise present in the system. The definition here is that NEP, noise equivalent power, is a ratio of voltage noise over this voltage responsivity. And its advantage is that it allows you to use compare different detectors regardless of the circuits used to convert intensity to voltage. So you can imagine that if I put an amplifier at the output of this circuit, I can increase voltage responsivity 1,000 times, but I will also increase noise. So NEP is more important characteristics than responsivity itself. Another thing I care about is the response time, especially for HERMES that wants to use detectors for transferring data. Response time has to be very small. And definition here comes through this simple differential equation. There is no actually better definition than that. So change of the signal depends on how far the signal is from saturated voltage. So if we switch on light, we get this slow time-dependent change of the output, which is exponentially tends to approaches the saturated value. And this power dependence is defined by one single parameter that has unit of time, measured in seconds or maybe femtoseconds. Nevertheless, is characteristic time of this system. Okay, so these are the three parameters we care about. Responsivity, we want it to be high to measure weak signals. More importantly, we want NEP to be low, and we want this response time to be small. Again, most important for sensitivity is the noise equivalent power. Commercial terahertz detectors have noise equivalent power of about 1 nanowatt per under root hertz, whatever it means. We understand that it's about nanowatt power that we can detect. And the voltage noise that has to enter the formula for NEP is in most research works approximated with using Nyquist formula, which has resistance of the detector multiplied by Boltzmann constant and by temperature, and you underroot this. This is the spectral density of voltage noise predicted within a pretty simple approximation, but it works in many cases. So it's intrinsic noise of the detector that has a certain value of resistance. Okay, key types of radiation detectors. In this talk, we will not consider anything sophisticated. We consider two types, photoconductor and rectifier, which is similar to photodiode. And importantly, I will provide just one example of terahertz detector based on graphene that operates as a photoconductor. Most of them are rectifiers. It's kind of clear to understand why. I will specify this a little bit later. So what is a photoresistor or photoconductor? You have an object that through which you feed some current, and this current depends on the applied voltage. And you have in Ohm's law to describe this dependence. Sometimes Ohm's law works for the object we work with. Photoresistor or photoconductor will change its conductivity significantly when exposed to light. So again, it's not a universal rule, but in most cases, resistance drops or conductance grows when you expose this object to light. So you have bigger current for any applied voltage or smaller voltage for any applied biased current. So in order to detect light with this type of detectors, you need to bias them. So you need to waste some energy on feeding this current through the detector. Okay, another type of which is photodiode. So I show a diode, real diode here, but I don't specify what is it made of at the moment. So important feature of this device is that when you expose it to light, the current voltage characteristics not necessarily changes this law, but what most importantly, it shifts with respect to original one. So actually, if you apply no voltage here, you can just, no bias here, you can just measure the voltage at zero current and you will detect light. So it's more comfortable, it's more energy efficient, and therefore that's what people really want from your detector. So when we work with visible range, photoresistors and photodiodes are based on semiconductors, and the main mechanism of light detection is excitation of carriers over the band gap. So I take some of your time by illustrating this with this, I hope, simple chart. So electrons from carriers from valence band are excited to conduction band, and that results in the increase of conductance. That's very simple, qualitatively very easy to understand, and that results in linear dependence of conductance on light intensity. But you need to use semiconductor, and over band gap excitation is the main mechanism. Very similar thing happens with the photodiode based on semiconductors. You have a p-n junction, p-doped semiconductor, n-doped semiconductor. They bring them in touch to each other. And somewhere here, where this red arrow is shown, you generate carriers, and then they split because of certain reasons, and that results in non-zero current with zero bias when you expose these things to light. So one, again, important thing, when you come to terahertz range, the energy of light quanta is smaller than the temperature at which you exist. And therefore, this over bandgap excitation will not change a lot in your system. So this approach doesn't work. And that's why gapless material like graphene turns out to be welcome. There is no, it will not provide any general reason why graphene is so good. I will just illustrate some examples and of using graphene there, and show that, and it will be seen, I guess, I hope, that you can make fusion detectors using graphene. I want to be funny for a little while and say that if you discover new material, there are three things you want to try with it: photodetector, chemical sensor, and memristor. You can check this for yourself. Like this MOS2, for example. You make photodetectors, chemical sensors, memristors. There are papers about that. And you may say that, okay, trying these things allows you to publish something with no actually commercial promise. It's just selling point of your paper. But in case of terahertz detectors and graphene, it's not just selling point. It's really something that can be used in the future to make efficient terahertz detectors. So let's talk about graphene for a little bit of time. So graphene is a zero bandgap semiconductor. So these things here show graphene band structure, dependence of energy on wave vector. Important thing is that we can shift the Fermi level by simply applying voltage to a circuit in which graphene is embedded. So this line here is graphene, this blue medium is dielectric, and these yellow things are electrons. So if you apply voltage between graphene layer and a gate electrode, which is close to it, so this distance is on the order of 10 nanometers or 100 nanometers, you can, due to charging this graphene layer, which acts as a plate of a capacitor, you change the Fermi level position because it's just a single atomic plane. When you induce charges, you occupy more and more states in the phase space, so you have to change significantly shift the Fermi level. And this chart shows one of the first conductance versus gate voltage measured for graphene. And it clearly shows that conductance goes through a minimum, and this minimum corresponds to what is called charge neutrality point, CNP, where Fermi level is about what in this very point that separates valence band, red, from conduction band, blue, for graphene. So it's very tunable material. That's also very important. And depending on the application, and I stress you, I pay your attention to it, that you sometimes can need to fabricate this gate electrode on top of graphene and separate it from the gate on top of the deposited gate dielectric layer on top of graphene. So here, graphene is on top of the dielectric layer, so it's easier to fabricate such structure. Sometimes you need to do extra fabrication steps to create this gate electrode on top of graphene. Okay, graphene itself comes from can be synthesized using different techniques. So it can be CVD grown on top of metal, copper or nickel, and then transferred on dielectric substrate. It can be also grown on top of silicon carbide, which is by itself dielectric. So these two techniques can be treated as something compatible with industry, but it's very difficult to gate graphene on silicon carbide. So it's difficult to extend this technology to some really industrial level. So originally graphene was discovered by exfoliating, which means you transfer one atomic layer of graphite onto a dielectric substrate by just peeling it off. I hope that most of you know how it works and understand how difficult it is. And then actually people discovered that you can get even better quality graphene if you encapsulate this exfoliated single atomic layer of graphite between two flakes of very good boron nitride flakes. So if you want to increase quality of graphene, you go this way, but it involves more and more sophisticated ways of fabrication. And when I say improve quality, actually it's a bit ambiguous because depending on application, you may want actually different properties. So when I'm showing that you improve quality, what I actually mean is that I increase the mean free path for charge carriers. I decrease the number of defects on graphene surface. Depending on application, it may actually be worse. But for fundamental physics, this is what you want to deal with in most cases. Okay, so I come to main papers related to graphene-based detectors, starting with graphene-based rectification. The work I want to start with was published in 2014 by a group of Michael Furrer, who was at the University of Maryland at that time. And, or maybe, never mind where he was. So they were using exfoliated graphene. And in order to make an asymmetric structure that is necessary to get this rectification effect, so important, they used asymmetric metallization. So this, in this case, graphene channel is contacted with gold on one side and with chromium on the other side. It's easy to do using shade evaporation. And importantly, graphene work function is in between these two values. So this is what is called contact doping. By bringing graphene sheet in contact with chromium that has smaller work function, you dope this part with electrons. So you n-dope this part. By bringing it in contact with gold that has bigger work function, you dope it with holes. So you p-dope this end of graphene sheet. The doping in between is defined by the gate voltage and by the whatever is atmosphere it's exposed to. So this asymmetric doping can have some resemblance to a p-n junction, because here is p-doped, here is n-doped. And what happens here is that when you feed electric current in this system, you heat this channel. In this case, it's graphene. And you can do it in two different ways. So what I show here is that due to certain asymmetry of the channel, one side is heated more than the other. So again, what I'm talking about is Joule heating of the channel induced by the terahertz frequency current that are driven here by this radiation to which graphene channel is coupled. So if the channel is uniform, there will be a voltage proportional to difference in temperatures. The proportionality coefficient depends on the material and its properties. And maybe if you can see from the formula below, it actually can be tuned by changing the gate voltage. This formula actually tells us this because with gate voltage, you change EF value. So something, as you change the Fermi energy, this term will also change. On the other hand, what can also happen is you can have the channel not uniformly doped. So the Z-back coefficient now can depend on temperature, and the voltage you will measure will be given by this formula, by integral over the length of this channel. So it's product of Z-back, local Z-back coefficient value by gradient of temperature. That's important to know. And in order to convince you that this thing actually does work, I want you to recall that there is an object which is called thermocouple, which we use to measure relatively high temperatures in furnaces and other things like that. When you have two metals outside, this is the same metal, and different metal inside, and you have different temperatures of these contact areas, you will have a thermoelectric power that is proportional to the difference in temperatures. So this is very well-known effect. And it occurs on microscale in many devices that are used to detect terahertz radiation. So again, Joule heating, the distribution of temperature is defined by the properties of the channel and the current that dissipates energy inside this channel. So this chart shows two different types of heating you may get. So one, if you have asymmetry defined by the contact resistance. So contact resistance is larger on the left than on the right, you will have elevated temperature on the left, and then you can estimate your response by this value. So it's just proportional to the temperature difference. On the right side, I show that the Joule heating results in temperature elevated in the middle because contact resistance, if contact resistance is the same, you would have bigger temperature in the middle because heat goes away to the contacts because they are metallic. And in the middle, which is far from either of these contacts, temperature will be larger. And in this case, if you have a p-n junction, once again, for photodiodes, p-n junction is used because you generate photocarriers there and they go away from the p-n junction into different directions. Holes go leftward, electrons rightward. That's the mechanism. Here, it's very different. You unevenly heat the channel, you heat the p-n junction, and then due to different signs of the Z-back coefficients for holes and for electrons, there will be a non-zero voltage generated here. You can say that heated region of the channel behaves such that main carriers escape from it. And then if this side is p-doped, holes will escape leftward, rightward, and if this side is n-doped, main carriers are electrons will escape leftward. So there is some similarity to photodetector based on semiconductors, but it's very primitive. So what they have shown in this paper is that if you have a symmetric distribution of temperature and some asymmetric distribution of Fermi level positions, so contact doping, you would have non-zero voltage in the channel, and its dependence on the gate voltage was very checked in this paper. And important methodological advantage methodological approach they were using. They checked what voltage you get if you just hit the channel. So you can hit this with a small frequency AC current and see the onset of DC voltage as the result, which, because in what I was explaining before, nothing was depending on frequency of the current that results in this Joule heating. Okay, so there is another way to create the asymmetry required to create photo-induced voltage. And in the work I'm presenting next, it is done by a split gate, double gate structure. So the technology required to fabricate this sample, this device, is more sophisticated, but it's worth it. So it was demonstrated that detector working this way is fast and sensitive. It's, once again, it uses split gate. You apply positive gate to one electrode, negative gate to another electrode, and that's how you get this p-n junction. I don't go deep into details of this work. I just want to show this picture. It's very nice. It tells you something about wave optics. So the detector is very compact. It's also very fast, but it's not illustrated by this picture. Its response is defined by this photothermovoltaic effect. So radiation hits the device. Due to p-n junction, you get non-zero photovoltage. And it's so compact and sensitive that you can do efficient beam profiling for terahertz radiation. That's what is shown in this picture. So this figure shows intensity as function of two coordinates inside this terahertz beam. Okay, this is work in which I participated. It comes from 2018. It's important for me because it illustrates two points. I start with configuration of this device. Again, we were inspired by this work by Michael Führer, and we were using contact doping, contact asymmetric metallization to create photovoltage at the output. We were using not chrome and gold, we were using vanadium, and chrome and gold. The vanadium has even smaller work function than chrome. And what we see is that, first of all, we compared bulk piece of graphene to a bunch of nanoribbons. We have seen the photovoltage in both cases. And what was really important in this case was the frequency dependence of this response. So at room temperature, in both cases, is you increase the frequency of the radiation, responsivity, which is voltage over intensity or voltage over power for this device, increases as you increase the temperature. It goes down actually as you increase the temperature, which is pretty bad, but sort of expected. There is some intrinsic resistance times capacitance that limits the time response time and maximal frequency to which the object reacts. But surprisingly, as you cool it down to liquid nitrogen temperature, which is not very low it's actually high, still higher than the light quanta energy for this frequency range. You see the trend changing to the opposite. As you increase frequency, the response increases, the responsivity increases. And it turned out that the only way to explain it is to introduce plasmonic response into the system. So if you solve the hydrodynamics and equation of motion within Drude approach, you get the plasma waves as solution to the equations. And that means that the channel by itself operates not just as a resistor, but it has intrinsic inductance and capacitance. Inductance is actually a kinetic one. It's related to the energy, kinetic energy of charge carriers for a given current. But there is capacitance that actually comes from plasmons. And then rectification takes place at a p-n junction, and you should model it as a diode shunted by a capacitor. And the mechanism of this rectification by itself is very interesting because Schottky diode operate due to band gap of the semiconductor that is embedded into them. Graphene is a gapless material, so why should we have any diode type effect here? And the explanation is very easy, but I think it's kind of beautiful. So if you consider motion of charge carriers and dispersion relation, it's just energy is just Fermi velocity times momentum value, but momentum value is calculated using Pythagoras theorem here, px squared plus py squared. Electron moves along x-axis, but if it moves at an angle, the py component cannot change because all the potential profiles, all the potential energy changes along x-axis due to contact doping. Nothing may happen to py. So what you get is some kind of gap type spectrum now for electrons that move at an angle. And for them, there is a classically prohibited region through which they have to tunnel. And the width of this tunneling region depends on the angle at which the carriers approach this p-n junction. That is a very beautiful effect. It has to do with the Klein paradox. And interestingly, graphene works as a Schottky diode because of this Klein effect. Okay. I don't know, Antonio, how much time do I have?
I think 5 minutes. It's okay. 5-10 minutes maximum.
Okay, 10 minutes. So I try to speed up. So I've told the most important part of my story, which is that rectification is important mechanism of terahertz detection when you use for terahertz radiation detection, and graphene is a good material for that. But more important type of rectification comes not from contact asymmetry or p-n junction. It comes from asymmetry of what is called boundary condition. So this idea that was originally published in 1993 by Dyakonov and Schur, not for graphene, but for any field effect transistor, is that when you couple radiation, terahertz radiation, with an antenna to gate and one of its source or drain, actually let's talk about drain for clarity, you have asymmetric boundary conditions for terahertz frequency currents, and combined with some nonlinearity in this system, it gives rise to photovoltage. So, and in order to observe this phenomenon, you have to actually go through a little bit more sophisticated technology. So you have to couple radiation via antenna. So one of the sleeves will be will work as the source electrode to the graphene channel. Drain electrode will be made by non-coupled to radiation. It will be decoupled from that. Then you want to fabricate another sleeve that made of that is a gate electrode. So you have to protect your channel from gate electrode with a dielectric. Then you deposit this golden top electrode, which is coupled to the antenna. So the first before I talk about how it works, just a few insights into the theory published by Dyakonov and Schur. So the very simple part of this is the following. By applying AC voltage to this system, you actually excite some AC current, which depends on the impedance of this antenna. And DC current will not flow through the gate dielectric, but AC current will flow in the system. And since the current itself, the conductance of the system depends on the gate electrode, there will be this non-linear term in the response of current to the applied AC voltage. And the responsivity of this device can be easily expressed if you know how conductance depends on the gate voltage. So you need high sensitivity of gate voltage to gate conductivity to gate voltage in order for your detector to operate and have good sensitivity. Okay, so more importantly here, they predicted that for high mobility channel, response will strongly depend on frequency. So it will be resonantly enhanced due to excitation of plasma waves. This effect is important from both theoretical and fundamental and for application. So the operation of transistors as detectors was demonstrated by a group of Wojtek now long time ago, and they were the first ones to actually try the same thing with graphene. So in this work published in 2012, first TeraFET, it's called TeraFET, field effect transistor to based terahertz radiation detector. It has its own name, TeraFET. So graphene-based TeraFET was first demonstrated in this paper in 2012. They were using, actually, I think exfoliated graphene with some trouble to do the top gate. Never mind about this. What they have observed is that the response of this device is really described by this Dyakonov-Shur formula theory, but with highly damped plasma waves, so no resonant effect. And interestingly, the noise equivalent power they have detected is slightly better for double-layer graphene than for single-layer graphene, but it's not as good as you are supposed to have for conventionally interesting detector. So I think that good rule of thumb is that the NEP noise equivalent power should be on the order of 10⁻⁹ of these units, which are watts per root hertz. But it was the first demonstration of TeraFET made with graphene, so it's an important milestone in the terahertz detector, for terahertz detector community. And interestingly, the detection mechanism here can be both related to this Dyakonov-Shur formula model and photothermoelectric effect, because you have both heating and heating of one side of the channel due to this capacitance related currents. And one of works where I was lucky to participate pretended to disentangle actually these two responses in a very similar graphene structure. So I think I skipped this because it's not that important. What is more important is that we succeeded in demonstrating tunneling as a tool to enhance detector sensitivity. Again, due to lack of time, I will try to skip some part of it. We were using double-layer graphene that has band gap sensitive to electric field, so many things can be tuned if you have several gates here, and you tune some geometry of the objects to enhance tunneling through the real now Schottky barrier occurring at one of the electrodes. And I skipped the formulas for tunneling. Why is this so much better? The result is that you use the same tunneling concept that allows you to win over Boltzmann theory for transistors to significantly enhance sensitivity of the detector. So this chart shows the responsivity of this structure. And when you open a band gap in this bilayer graphene by applying double electric field across perpendicular to the channel, you increase the responsivity from what is described by this black curve. So you don't even see any, you hardly can see any amplitude of signal here. You enhance it to this or that, depending on the sign of the electric field you apply to the channel. So it's very beautiful effect, nice work. And also, again, quite briefly, the resonance dependence of response on frequency was demonstrated in another work where I was lucky to participate. But what was actually changed in this work, not the frequency, it was changed. We have done measurements for several, quite actually few frequencies. And at large frequency, we see pronounced oscillations for when we sweep the gate voltage, tuning the phase velocity of these plasmons and demonstrating that response is defined by a Fabry-Perot interference of plasmons inside this channel. That's, again, a very beautiful story. It has some application potential, but I'm coming closer to the end of our story. I have to show that photoresistor based on graphene can also be made. So this is an important work coming from 2016, done by good colleagues, and it demonstrated quantum dots, nanodots made of graphene. This is graphene on silicon carbide, where you can etch but cannot gate. So you see the structure. These are sleeves of antenna that is coupled to a very small piece of graphene. And when you measure the IV curve of this system, with and without radiation, you can get very significant change of voltage for a fixed current, because radiation changes temperature of this dot and therefore changes its conductance. So graphene itself, being a gapless material, has resistance that is not very sensitive to temperature. But if you confine carriers inside a small structure, it will have carriers will be energy of the carriers is quantized, and therefore transition between this from valence to conduction band happens via excitation, but not actually light-induced excitation, but via temperature. And this so quantized energy acts like a band gap, and when you couple this object to radiation, its conductivity now is very sensitive to temperature and therefore to intensity of radiation. And they demonstrated a high, very record low noise equivalent power. So it's very, very sensitive detector. Okay, so now I show a few slides about what we are doing in UEF. So this is our working place when we do work, so it's kind of messy, but it shows that people do work here. So currently we just fabricate structures that are not going to be used for HERMES project itself, but are very good to characterize quality of the device. So they are shown here. The antenna is tilted. It's a low tie antenna that is tilted, and such structures have been shown to work as helicity sensitive detectors. But for us, important is that they are sensitive to light polarization. So, and the sensitivity to light polarization tells a lot about the quality of the graphene channel. So that's the setup and device setup we use in order to adjust, to optimize quality of the graphene channel that we're using to detect radiation. So that's beginning of our long journey towards happy end of HERMES project, which will result in transceiver. And here I list some messages. So graphene-based detectors are more than just pay per selling point. That's important. Currently achieved key parameters are comparable to those of commercial detectors. And actually our current approach is that we want to achieve good results with CVD grown graphene. And for mechanisms of detection, I already discussed them. And currently our work is dedicated in UEF to graphene integration and to terahertz detectors. So that's some further reading. And I thank all of you for your attention.